Good morning, everyone. We look at Earth and we see a biosphere. We see it teeming with life, and we know it's got a complicated history. And then we look at Mars today, and boy, it sure doesn't look like it has a biosphere. You know, from a distance, it looks like a barren, dried up red rock. And for a long time, that's pretty much where that perception stayed. But it's changing. This is Mars today. Earth wasn't the same in the past, neither was Mars. Now, these are two artistic renditions of what we think they might have looked like, and I'm sure that they are both very wrong. Earth both planets were being hit by lots of meteorites during the late heavy bombardment around 4.2 to 3.9 billion years ago. And there was lots of water around. It fluctuated, it came and went because the surface of the planet was going through all sorts of havoc. But this is the time when most scientists are feeling very confident that life probably got going. This is the time when life went from some crazy, messy chemistry that we don't know what it was to something we would actually call life. And we don't know all the details in between, but this is when it happened. If it happened on Earth at that time, perhaps it happened on Mars. So let's run with that assumption, because really this is at the heart of why we think there might be life on Mars. The biggest difference between the two today is the magnetic field. Earth still has its magnetic field, which means it's protected from ionizing radiation, but not so for Mars. Mars lost its magnetic field sometime during the late heavy bombardment around 3.9 billion years ago, and when that happened, the solar wind from the sun, which at that point was very strong, blasted the atmosphere away. But that wasn't it. It also exposed the planet's surface to all of the radiation from both the sun as well as the galaxy. There's two really important components. No, the atmosphere was being blasted away continuously. So imagine you have volcanoes and rocks and they're still spewing some stuff out into an atmosphere. The atmosphere is slowly being stripped away constantly over time. And the surface is being exposed to the radiation. This complicates what might happen in the evolution of a biosphere. Let's talk more about that radiation. There are two important components. The first one is electromagnetic radiation. So here's the spectrum, and you can see in the red it's marked non-ionizing. This is the type of radiation that we're used to in our everyday lives. It includes things like power lines, the radio, microwave ovens, the heat that we use to heat up our homes and offices, visible light, what we use to communicate with each other. And it also goes into ultraviolet. However, at the top end of the ultraviolet light, we enter what's called ionizing radiation. And we're familiar with this because this is the UV that causes cancer in our skin. And that UV can actually change the molecules in our skin. But ionizing radiation on Earth also includes X-rays, like what you get at the dentist's office, as well as gamma rays that might come from radioactive sources, both natural and man-made, or microbial sterilization. We use it all the time in laboratories. We use it for our food and our food packaging. Okay, these things are, you notice the range that we go up to. And then you see that big, beautiful purple and red and yellow picture there. That is from the EGA instrument where it measured the gamma radiation in the galaxy. What you're looking at there is the Milky Way. But you're looking at it in the terms of gamma radiation. And that's not normal gamma radiation like what we see here on Earth. That's radiation that has an amazing amount of energy. Do you see all those squiggly lines up there? You see how they're long on the left-hand side and they get shorter and shorter to the point you can't even see them on the right? That gives you an indication of how much energy is in the electromagnetic photon. By the time you get over here to where you see that picture, you can't even see the squiggles. There's an amazing amount of radiation, there's an amazing amount of energy in those waves. They're photons, and they have all this energy. This stuff is all over our galaxy, and it comes into our solar system. On Earth, we're protected, not on Mars. So let's talk about that type of radiation. I'm talking about the photons, which is the UV, the gamma radiation, the X-rays. That radiation comes in, and there's a direct effect on an organic molecule. In this case, we're talking about DNA. That radiation comes in, it hits an atom of some sort, it throws off an electron from that, and that electron then hits a bond. A carbon-carbon bond, carbon-oxygen, carbon-nitrogen, anything. It hits a bond, and it breaks it. It throws an extra electron in. It breaks the bond. That's direct. The indirect is you have radiation come in, does the same thing, but instead of that electron hitting something like a carbon-carbon bond, it hits something like water or perchlorate. And it produces a free radical. We know about free radicals. We talk about them all the time for our health. Free radicals do damage to things by reacting with them. And it's not like you have an oxidant that reacts with something else. This is an entity that has energy, and it's so unstable, it's going to go, and it's going to react with something super fast. That's an indirect method. Both of them produce damage to organic molecules. But there's another type of radiation that we need to talk about. So you can see up here on the left hand, you see the squiggle, and then there's that first dot. That first dot is the electron we just talked about. Two more over, where the arrow is coming out, is a proton and a neutron. Notice the size difference. It's huge compared to the electron. And in cosmic radiation, protons make up 89% of that radiation. That's a lot of protons. And they have a lot of energy. When a proton hits something like DNA or another molecule, it does a lot more damage. Not only that, but it has a cascade. That proton hits something, and then it produces gamma radiation and also electron radiation and some other types of particles that can do further damage. So there's a distinct difference between these two types of radiation. Now, when we talk about the Martian surface, and you take, for instance, the electromagnetic radiation, the dose, the amount of energy deposited onto sediment or any other material is going to be greatest near the surface, where the radiation comes in and encounters the surface. That's the pink line, as an example. We think of this a lot of times in terms of UV, but gamma and X-rays do this too. Now, when it comes to things like protons, neutrons, and other ions, it's different. They have energy and they have ability to penetrate into the material, and as they come in, they actually strip off electrons and they lose their energy, and at some point they slow down to the point where they just stop. And so you end up with something like this red line, where it's low, the dose is low in the beginning near the surface, and then as you get deeper down, the penetration depth, it goes deeper down, you get this peak. We call it the Bragg peak, where you get this amazing amount of deposition of all these protons. So you've got energy deposition, and you've got mass deposition when it comes to particles. And sometimes if you've got changes in the types of materials, you're going to get something spread out more like the blue one. Now, the depth that happens is dependent on the amount of energy. And what we know from the surface of Mars, from the RAD instrument, at least for protons, is that we've measured some of that. And it's pretty close, not exactly what was predicted. And you can see the black lines here are the actual measurements for 0 to 100 mega electron volts of proton radiation. And there's a flux there. We use this for modeling what happens at the surface, how much radiation comes down. And to approximate what the rest of it looks like into higher amounts of energy, we have the red line, which is a model. And notice that it extends from 100 to 500 mega electron volts per proton, and it stays pretty high all that time, which means that when we go back to this, the penetration of those protons can actually vary. That Bragg peak, imagine having a dozen of those for different types of energy levels. Now, when we're on Mars today, it is easiest for us to drill shallow, to look for what the history of the planet was like, to look at what an environmental chemistry might have been like through the rock record. And on MSL, we drill down about 5 centimeters. That's roughly equivalent to the peak, the maximum dose from the electromagnetic radiation, but not necessarily the proton radiation. How much damage do you think that proton radiation does? Well, I set out to find out. And I took some rock material. One of them was just silica. Another one was some clays mixed with basalt. I call that the analog 1 here. And I mixed in some molecules. Those are listed on the left-hand side. These are free molecules, so they're just standards mixed in with the sediment, and then I expose them to 200 mega-electron-volt proton radiation for what would be approximately 4 million years of exposure on the surface of Mars. That's nothing compared to what we think the rocks on the surface of Mars have experienced. And what all of those bars are showing is anywhere between 20 and 100% loss of those molecules. Depends on the molecule, depends on the chemistry of it, depends on if you have perchlorate mixed in. When you have perchlorate mixed in, you get more of that free radical damage, more of loss of the molecule. There's another type of organic matter on Mars, though, and this is probably more likely. 90% of all organic matter that we find in nature, whether it's on Earth, in a meteorite, anywhere else, is macromolecular carbon. And what that is a whole bunch of small molecules that have been put together into one massive molecule. They're bonded together. It's just big gloppy stuff. We call it kerogen in the rocks. So I added some kerogen to the same types of sediments, and I looked to see what happens to that. Well, it ends up that for different molecules, it also starts, that material starts to break down and releases small components. And what I'm showing here is the release of things like phenanthrene, which is a pretty big molecule in terms of biosignature sometimes, and phenanthrene and pyrene. These things are the typical things that you would expect from a kerogen. And what it's showing is that we're actually breaking down the structure with the radiation exposure. So the point of all of this is to say that, hey, we predicted that this was going to happen, and now we've got data that shows it. This is what the proton radiation is doing. I didn't even use UV or gamma ray or X-rays or any of the other stuff. So when we go back to looking at those curves and the penetration depth of where we want to look for signs of life, if we're looking at the rock record and looking for something old from an ancient environment, we want to go deep. The green line there marks the best place to look. We want to go past that Bragg Peak. If we're looking for a life that's living there today in the rocks, because it wants to stay away from the radiation, which is so damaging to its DNA or whatever it's using to live, all of its biochemistry. Best place to probably look is below that Bragg Peak, below penetration depth of about 2 to 3 meters. And that depends on which model you use. We're only working on models so far. So if life got established early, did it adapt to the challenging conditions of this planet? Did Mars have habitable environments in the past? Jen Stern was here yesterday, and she talked about some of the work that's been done on this topic. But I'm going to give it a short little spin and leave the details to her talk. I'm going to start with the Burns Formation that was observed by Opportunity rover. And this is an aeolian deposit in which groundwater came up and deposited a bunch of minerals. Groundwater, liquid water. This was in 2005. We finally had suggestions of liquid water. Hey, life needs liquid water. Perhaps life has used it in the past when this was formed. Perhaps it's using it today. So then in 2012, I say the search got restarted, meaning we did search for life once with Viking, but it was a while ago, 40 years. And so we sent MSL, the Mars Science Laboratory, with a Curiosity rover. I'm sure that a lot of you in this room remember this moment. I certainly do. It changed my career. It changed my life. I've never been more excited and had a bigger adrenaline rush than this moment. So, we want to search for ancient life. This comes down to 3 questions, 3 steps. Were the environments in the past habitable? Meaning, could they have supported life? How so? Habitable is not a yes or no answer. It really has a gray area in between. We're starting to address this question, and we're really at the yes or no area. But the details matter, and that's what we're working on now. Second one is, could biosignatures have been preserved? And the last one is to look for biosignatures. And MSL was never prepared to look for signs of life. It is not a life detection mission. It's focusing on the other 2. We need the other 2 to know where to look, to know what problems the chemistry of Mars might impose on our instruments. So we have MSL on the ground, and lo and behold, the planet's not red. Boy, were we fooled. We've been looking at Mars for so long from space, for the Hubble and all these other great spacecraft. It's a red planet. It looks like a red rock. It's not. It's a gray rock. It's a gray rock, and it has a layer of dust on it that is super, super thin. It's gray underneath. There's a whole story in here, and we had no idea. We found mudstones. Mudstones are great for preserving stuff because it's really fine-grained material, and it's hard to get other stuff in there to destroy your organics once they're in there. Radiation can still penetrate, but the water in the ground cannot get in there as easily. Great place to look. We found loads of them. And we looked, when we finally got past Marias Pass, as we were at the very bottom of the mound, we looked up, and this is what we saw. This is our route forward as we're heading up the mound in the middle of our Gale crater. And we were able to look at this and determine the stratigraphy of it. And you see where I have this green Murray formation? That's the mudstone at the base of the mound. And we saw it down there, and we got some fabulous data. I'm going to show you a little bit of it in a second. But that mudstone, it's a package of rock that's 200 meters thick. 200 meters. Mudstone requires quiet water in order for fine particles to settle out. What does this mean? Most likely, the Gale crater was filled with water. And it was probably shallow, based on what we see in the sedimentary rocks. I'm sure it fluctuated a lot. Up and down, up and down. We don't know exactly how long it was there, but it was probably there quite a while because to get a 200-meter sediment package takes a while even on Earth. I'm sure it took a while on Mars, long enough that we call it geological time. Now, what's crazy about all of that is that we found organic molecules there too. We found them in Yellowknife Bay, but there we found mostly chlorinated molecules and only a few. It's different here. We've got evidence of sulfurized organics. These include things like methanethiol, dimethyl sulfide, thiophene. And I'm not going to explain all the details of this measurement because Jen Stern talked about evolved gas analysis yesterday. But the point is that these molecules that we're observing don't come off the sample until you heat it to about 600 degrees. You can't get that from any kind of contamination. It's not possible. We confirm the presence of those molecules with GCMS. So here they are, and I'm showing in the red is a blank. You don't see much in it. In blue is our sample, one of the samples that has these molecules in it. You see the big peaks in there. They're the same molecules that we predicted from the other analysis. And then we went back to our SAM breadboard and we ran it the same way and with standards and confirmed that the times that we see those peaks are indeed the molecules we think they are. But it doesn't stop there. We've got a whole suite of aromatic hydrocarbons. Granted, they're mostly single ring molecules, but there's a whole suite of them. And again, they're coming off above 600 degrees, above 500 degrees and sometimes 600 degrees. And then there's another suite of alkyl hydrocarbons. These are the long chains, the things that you think about when you think of lipids, but these are just short little pieces because we can't actually identify the molecules that have a long signature like that with the method that I'm using here. This is evolved gas analysis. We could in GC, but we didn't see them there. There's not much here. What we are seeing are little clips of carbon chains, and they go up to carbon 5. You can't get carbon 5 from the contamination. You can't get it from the SAM organic background signal. These are most likely coming from the sample. So we've got sulfurized organics, aromatic hydrocarbons, and these alkylate hydrocarbons. These are the exact type of things we would expect if we had a macromolecule that had sulfur in it. This happens on Earth all the time. Sulfur protects the organics inside the macromolecules from breaking down. It stabilizes them. We came up with a way, we have identified a suite of organic molecules that tells us that there's a way of preserving organic molecules on Mars. Okay, check. That was on our list. What does that tell us? Well, there's 4 different types of organic materials that we might be looking at. And we can't tell which one we have. First one is interplanetary dust particles. This stuff is raining down on the surface of Mars all the time. think of a snowflake coming down and landing in a football field. It takes a lot of snowflakes in order for it to accumulate, but over millions of years, we can get that. We could be looking at that type of material. This is the same type of stuff as meteoritic carbon. There's also evidence from meteorites from Mars that there's hydrothermal carbon and also this other macromolecular carbon that's geologically made in basalts. It's possible we could be looking at that. And the last one is microbiota. What if it was life in the past and that organic matter went into the sediments and went through some geological processing and turned into these big macromolecules? This happens on Earth all the time. And it is this type of a material that gives us oil and other petroleum. This is what we live our lives on. Okay, so it's very possible this material is the same, but we cannot tell. We do not have that type of information. So how does this all relate back to the chlorohydrocarbons that we saw at Yellowknife Bay? This is the stuff that Jen Stern talked about. When you have macromolecules like what I'm showing in purple, and you expose them to ionizing radiation and oxidants, perhaps with some metal catalysts, which are all over the surface of Mars because it's basaltic, you go through what's called a Fenton reaction, and it breaks that material down. It adds a whole bunch of oxygens to it. And if you have chlorine around, instead of oxygen, it can be chlorine added to it. And you get small little components that are much, much, much more stable on the surface of Mars. And when we analyze those in the SAM instrument, they come off at low temperature. That's consistent with what we saw at Yellowknife Bay. There is a consistency to the observations that we have made in Gale Crater in terms of organic molecules. That leaves us with looking for biosignatures of the past on Mars. That's the next step. We have already said we've got all the key elements we need for habitability. We know we've got a way of preserving it. So the next step is the next mission. And we've got 2 more talks coming up that are going to address that. But that's not the whole life story. Is there life on Mars today? We've got evidence of transient liquid water on Mars today. This was a new finding. I'm sure many of you saw this. There's actually 2. This observation here of the reoccurring slope lineae that was observed in high-rise. And you can see those tan brown lines coming out. That's water and salt mixed together that's coming to the surface. Those are temporary. They come to the surface, there's some flow, and then they go away, and then they come back later, and they go away, and they come back later, and they go away. What I'm not showing here is that the MSL instrument also detected water in the form of liquid water that was coming out of the ground and turning into frost. It only comes out at night because during the day, it warms up enough and the pressure is such that it just evaporates right off and goes away. But the point is, it's soil moisture. We have liquid water on Mars today coming to the surface in key places. What's important about that is that perhaps that water is bringing organisms up to the surface. Maybe. It's a stretch, but it's a possibility. The other one is that that water could then fuel life. It could bring things to life if it's at the surface. Might be a stretch. The radiation is pretty intense, but it's possible. You know, we think of life not being able to tolerate radiation. I kind of think that we should keep our mind open and maybe life can tolerate that radiation. So why do we even ask if life exists on Mars today? I think there's 3 really important questions that we need to address, or 3 reasons. One, it's obvious, we're curious. Humans have been asking if we're alone in the universe for a long time, right? I'm not gonna get into that. The next one is we're talking about sending humans to Mars. If we send humans to Mars and there's biota there, and those biota are toxic to our humans, we're gonna have a problem. We need to find out. The next one is, if we want humans to go and stay for a long time, people have been talking about having them stay, live there for, their lives, maybe settling there permanently. That only works if you establish an ecosystem. It might be inside, but it's still going to involve Martian materials. We can't live there alone. If we're going to have humans live there for a long time, somehow the 2 have to adapt. Humans have to adapt to the life on Mars, and the life on Mars has to adapt to us. The more we know about that life, the better off we'd be. Okay, and with that, I will answer questions if there's time. And suck up. Didn't suck. Yes, go ahead, Jim.
We're going to go to the mics for the questions.
Oh, okay.
So we can get it on the recording. And I have one question, then Dr. Green, of course, you can ask the second question. Where do they think the recurring slope lineae liquid is coming from? Is that hydrothermal vents underneath the surface, or?
We don't know. There's lots of possibilities, but the salt that's involved is one that absorbs water super easily. I mean, it really kind of blows your mind away when you have the salt and any water molecule that comes by is going to just stick to it. And so there's a lot of possibilities, and we haven't been able to constrain that yet. Most likely it's still coming from below rather than up above because of the nature of the actual slope lineae.
So I wanted to ask Jen, for Mars 2020, we have a set of candidate landing sites. And those have been talked about and thought about for the last several years. But the new observations from Curiosity, the understanding that Curiosity is sitting in an ancient environment that in its past could have been habitable, might we find other areas like that? So the new observations, how is that informing us to really look through that list again and say, these are the better sites?
The two key observations that come with the presence of the organics, and I think that is sort of like a honing point for us in terms of looking for signs of life, even though we don't understand what they're from. It was sulfur and some mudstone. That's all we have to ride on right now, sulfur and mudstone. And the thing is, with the sulfur, we suspect it's a lot of places on Mars. And I don't think we're going to see it all from orbit, because right now we don't have the orbital signatures in Gale Crater that it's there. So it's a tough one. And I'm not so sure that it really helps the search, except to say that having a big package of mudstone helped. But the problem with mudstone is that it can also weather. And we've got plenty of examples where that mudstone didn't tell us a darn thing. So it's hit and miss.
Hi, I have a very basic question. Looking at the fact that there are so many similarities between Mars and Earth is living, Mars is dead, would you think, just because you are dealing with so many matters concerning Mars, that the main difference is the size, the low mass, the low gravity, which makes escape the atmosphere, the loss of heat being it? Do you think this is the main difference?
That's very possible that is the main difference. And so when the magnetic field was lost, it could have been lost because of two reasons. It may have been a combination of the two. One is that it's so small that it didn't have enough interior radioactivity to produce enough heat to keep the inside molten core liquid and started to solidify. We know that the convection stopped, and that was why the magnetic field went away. But there's also suggestions that there were impact events, and somehow that disrupted the core and helped exacerbate that process. So yes, I do think size matters, but how it actually mattered in its role in the loss of the magnetic field is uncertain. As far as the rest of the planet goes and its chemistry, and its physical environment, I don't think size made that big of a difference. It was really had to do with the magnetic field loss.
Thank you very much.